So now let's do a practical demo of bringing the ideas together. In my grad school research, an important chemical I worked with was LaMNO3, which could be made from mixing an appropriate amount of La2O3, Mn2O3, and mashing them together and then heating to over 1000 degrees Celsius. Now, let's say that in said research, I needed to generate 50.0 grams of this product. What portion of that mass is going to come from La2O3 and what portion comes from Mn2O3? Is it just going to be an equal split, half and half? No. That would be like saying I need equal masses of ham, cheese, and bread in my sandwich. That would be a up sandwich. Because again, slices of different ingredients have different masses. I really need to think in terms of slices to put that ham and cheese sandwich together. Similarly, in chemistry, I need to think in terms of moles. That's where we can directly compare the amounts of reactants and products. We can't do it in terms of masses because each of those reactants has a different mass from one another. So just because I have equal number of moles of each reactant, which is what I need according to the mole ratio, doesn't mean I'm going to have equal masses of each reactant. So here's how to approach this problem. Since I can't just directly compare masses between chemicals, but I can directly compare moles, first thing I need to determine is how many moles 50 grams of that product equates to, and I will use the molar mass. Hopefully you're already familiar with how to do this. That right there is the molar mass of LaMNO3, which you can look up for yourself or calculate it using the periodic table. That molar mass is stating that for every mole of LaMNO3, I must have 241.84 grams of that chemical. Notice how I've organized this. I've put grams on the bottom so that grams will cancel with grams over here, and I'll be left with moles up top. And so if I plug this into my calculator, I will get 0.206, and this is a 3 sig fig answer given the numbers that went in above. But because the problem's not going to end here, I'm going to retain one extra digit from that calculator answer, and that next digit is a 7. And I'm going to make it tiny to represent that ultimately these three numbers here are the significant ones, and this is just some extra data that we're going to carry over until we're done with the problem. And because we've set our dimensional analysis up correctly, we will be left with units of moles of LaMNO3. Now let's talk about how much of each reactant I need to generate this product. And I'm going to start all the way on the left, because why not? Now, the mole ratio states that for every mole of La2O3 that I react, I'll get twice as many moles of LaMNO3 as a product. In other words, if this is how many moles of product I'm going to generate, I just need half that number of moles of La2O3. The mole ratio says that we have 2 moles of LaMNO3 produced for every 1 mole of La2O3 that we use. Notice that once again, the units that I'm starting with and trying to get away from will cancel, and when I do the math, I'll get 0.1034 moles of La2O3. Notice again the sig figs. Just as surely as this is a 3 sig fig number, this is also a 3 sig fig number, but I'm still keeping one extra digit of data because I'm not done with the problem. And this mole ratio here is considered a set of exact numbers. There are exactly 1 moles of La2O3 for every 2 moles of LaMNO3 that are produced. But now I have the number of moles of La2O3 reactant that I need to generate this much product at the end of the day. Now, as a quick aside, if I wanted to know how many molecules of La2O3 that represents, I would just take that and multiply by Avogadro's number, where we say that there are 6.022 times 10 to the 23rd molecules, I'll just abbreviate it like so, for every mole of the species. And if I plug that in, I'll get 6.22 times 10 to the 22nd. That's how many molecules of this chemical we're actually going to need to make this much product at the end. But again, who wants to think in terms of this when we could just use this number here? So now I'm going to use the molar mass of La2O3 to figure out what mass of this reactant I ultimately need to get that many moles of La2O3. Again, I do this by using the molar mass, but this time, the molar mass of this chemical is going to be 325.81 grams, and I get a mass of 33.7 grams of La2O3. Notice I am finally rounding to the appropriate 3 sig figs, because I'm done with this part of the problem. I have found the mass of that reactant that I need. And this mass can easily be weighed. And according to the math that I've done, this mass corresponds to this many moles. And if I put in this many moles, I'll get twice as many moles of product. And that many moles of product right there corresponds to 50 grams of said product, which is what I was trying to produce in the first place. Now I could do the same type of math to figure out how many grams of the other reactant I need. That being said, there's a shortcut. Since I know that my final product must be 50.0 grams, and I know that 33.7 of those grams are ultimately coming from the La2O3, well, conservation of mass tells us that if I subtract one number from the other 16.3 grams must be coming from our other reactant. Because this remaining mass must come from somewhere, and the only logical explanation would be it comes from this other reactant. And again, I can weigh these masses out easily. But look at how different those two numbers are. How would I have ever learned what those numbers needed to be if I didn't have that mole middleman? From that reaction and the mole ratio, I can tell that I need equal numbers of moles of each reactant, but I cannot say that I need equal masses of each reactant. It's just like how I can say that I want equal numbers of slices of ham and cheese for my sandwich, but that doesn't mean that I want equal masses of each. Different ingredients, or in this case, different chemicals, have different masses from one another. And yet, if I didn't think in terms of masses, how could I possibly measure out that particular amount of La2O3 and that other particular amount of Mn2O3? I need both concepts, mass and moles, to do these kinds of problems. And this, again, is a very practical type of problem we might do in a lab. So to summarize these 3 different ways of quantifying the amount of a chemical, we have the objective number of atoms or molecules, and this is what is literally present, but it's not too useful practically. It's just good to understand on a fundamental level what's really present in these samples. Then we have moles, which is easiest for discussing the numbers of atoms and molecules involved in a reaction, and how they relate to each other. Like how we were able to say with the previous reaction that we needed equal moles of each reactant. Whereas mass is actually measurable, unlike these quantities. However, we cannot directly relate how the masses of atoms and molecules in a reaction relate to each other, just like we couldn't look at that reaction and say, hey, we need equal masses of each reactant. That was incorrect, as we saw.